Welcome to Lesson 2, Example 3. And they want you to determine the reaction R and the moment M at the support of the cantilever beam shown above, neglecting the weight of the beam. And they show a beam like this, and say you show fixed. And on a fixed end, you always have three reactions. You have the vertical reaction, which you can usually label V or R, whatever you want to do. You can actually name it whatever you want. You have a P or an FX, whatever you want to call it, one going horizontal, and then you have a moment, and that's at fixed reactions. So I've go ahead and thrown out this free body diagram, and what we're going to do is they're asking to solve for the reaction R and M. So we're just going to do that and try to go ahead and do the free body diagram, the shear diagram, and the moment diagram. Alright. Start out with your equilibrium equations as always. I'll go back. You have some of the forces in the F direction, or in the X direction, equals 0. I'm not going to write out the three equilibrium equations, so hopefully you know them by now. And we know there's no other horizontal forces except P, so P equals 0. There we go. P equals 0, so we can pretty much get rid of that. Then you have the sum of the forces in the Y direction equals 0. Because we only, the reason I did this first, as opposed to usually I do the moment first, is because there's only one unknown in the Y direction. So we're going to go ahead and do that. We have positive R, and then we have negative 500 pounds. And then we have an equivalent load. We have to make this 200 pounds. So 200 times 10, I'm just going to do it in my head, is 2,000 pounds. Remember, that's an equivalent load for that distributed load. And it's at 5 foot. Hopefully you just know that. And I'm not going to write that. I'll go ahead and put at 5 foot, if that helps. And that's 5 foot from the face of the wall. And let's go ahead and solve for our... Actually, we don't need to do that. What do you have? Negative 2,500, so that's what it should be. We don't need to use a calculator. R equals negative 2,500, then you put the negative 2,500 on the opposite side, so R is going to equal a positive 2,500 pounds. So we've gotten R, now we have to get M, and you just want to do the sum of the moments about, let's call this point A. Sum of the moments about A, say that this is positive, equals 0. And let's go from left to right. You have 500 pounds, and that's going to be a negative moment. So let's just say negative 500 at, what, 6 foot? Plus, let's just go ahead and say minus, since we know this is going to make a negative moment, since it's the same direction as 500. Negative 2,000 pounds times, we know that's at 5 foot. And then R is going to induce what moment? It's not going to induce any because it is concurrent with A. So it will not induce in the moment. So we're done. We don't have an unknown. Oh, we're not done. We have M. And we haven't done that before. We're not done. We have M. And M is in the negative direction. So we have a negative M. Alright. Now you solve for M. Let's go ahead and throw M on the other side. So you're going to have M equals negative 500 times 6 minus 2,000 times 5. And that is 13,000. That's a negative 13,000. Negative 1, 3. And that's foot pounds. And those are your answers. You have R equals 2,500 and M equals 13,000 foot-pounds. Let's go ahead and check that. R equals 2,500, and M equals 13,000 foot-pounds. Alright, now let's move on and do the shear and moment diagrams. Let's go ahead and put those on there. Let's clean up this free body diagram to make it look like we want to look. Now remember, you want to get your distributed load back, and you want to inflate your R. You can go ahead and get rid of P since it's equal to 0. Let's go back. Here we go. Let's change it back to white and say this is 200 PLF. We had an M equals, let's go ahead and put that in blue, 13 foot-pounds. And something I didn't mention earlier, notice this is negative. We need to go back and change this convention here. And let's see if that makes intuitive sense. If we, well, I guess that, and I said, no, I gotta go back to my pen. I said it was going to go up like this, but now, since it was negative, now it's a positive in this direction. Does that make sense? Yes. These are all going that way. This needs the resistance, so it's going to go that way. And that should make sense to you. Alright, where were we? Oh, reaction. We have 25,000 up. Since that's what we assumed, and it was positive. There we go. Now we can kind of get rid of this, so it doesn't confuse us in the future. Alright, there's our free body diagram. Some people I used to do in colleges do F, B, D, just to label it. Then you do VX down here. And then MX. And just to kind of guesstimate what we're going to get here, let's just guess. It's going to go 2,500 pounds up, and it's going to be going down. So you're going to want to be going up since we're going backwards. And it's going to go like that, and then it's going to come in right there. That's my estimate. And let's just go ahead and start it off and see what we get. I'll estimate the moment diagram. Erase. Alright, here we go. Okay. We're going to start at 0. And here's an important point at 6, and then again at 0, I'll call it. We'll just go from here, or 4 and 10, let's say. So we have 4 foot times 200 pounds equals 800 pounds. And that's going to be going in the negative direction, so we want to say negative 800. Let me go to 4. Let's go a little bit further, since we're kind of spaced over here. This is negative 800. These are all going to be pounds. These are all going to be foot pounds. So we won't label them on here. It just takes up a little too much space. And I'm going to put this over to the side. 800. Then we're going to go down 500. So that's what, 1,300? Say right there is fine, negative 1,300. Then we continue our journey down. Since this is a distributed load, our slope is going to be what this distributed load is, 200 pounds per linear foot. The slope is a negative 200. So 200 times 6 is 1,200. 200 times 6. And we're going to subtract that from 1,300, so it should be 2,500, which it is. You have 2,500 down here. So you continue the same slope. These slopes should be the same, but I'm just freehanding this, so they're not perfect. Yeah, 2,500 pounds. Didn't need to label that. And then we go up because of this 2,500 pounds right there. Alright, there's our shear diagram. Now we go in. We're going to do the moment diagram. Let's go ahead and divide these into shapes. And this shape, and I'll call it A2. That wasn't really very good at representing what I wanted to do. I'm doing dash line just to help out. This entire thing is A2, and this is A1. So let's see, we're got 10 minutes. I think we'll be good, or 5 minutes rather. A1 equals 1/2 because it's a triangle. Then it's 4 foot, and then it's negative 800 pounds. LBS. There you go. And what is that? 3,200 times 5, so it'd be 1,600. Let's do it on the calculator just to be sure. 1,600 pounds. That's negative 1,600 foot-pounds. So it's starting at 0 and it's increasing more as it gets to negative 1,600. And when you're doing this, you have to kind of keep in mind, hey, I'm not increasing as big as I am over here, so you can kind of settle down the slope that this parabola is going. So, because you're going to have to represent it bigger over here if you want to be accurate. In the end, it doesn't matter. 1,600. All right, now let's do A2. Now A2 is combined of two different shapes. We will first do this shape right here. We'll leave the triangle for a second. And that is negative 800. And that's pounds. It is 6 foot long. Let's just break it up into two. So 800 times 6 is 4,800. Negative 4,800. Foot-pounds. And then the other section, which is, let's go ahead and change colors real quick, which is right in here, this triangle. Let's call it A2.1. Is 0.5, since it's a triangle, times 6 foot, and then it's 13 minus 8, which, well, no, scratch that. Oh, actually I messed up. If you'll look, this was actually 1,300, not 8. Let's get rid of that, get rid of this, and recalculate. What would be 1,300? Negative 1,300. So 1,300 times 6 is negative 7,800. Alright. And then this is 25 minus 13 is 12. 1,200 pounds. And that equals 0.5 times 6 times 1,200. 3,600. And we need to add these two together to get our answer. We need to add this one and this one. And this is negative. I didn't put that in there, but it is negative right there. So 7,800, 3,600 is total. The sum is negative 11.4 foot-pounds. Now we want to go in there and say, alright, we had 1,600, negative 1,600 minus negative 11,400 equals 13,000. And you start, you're increasing a lot more than this. And that's why you have to watch what your slope is if you want it to be accurate. But you're ending with a little bit more increase. So this is a parabola. And I know it would actually start at a greater negative slope than this right here. But it's not how we drew it. So that's okay. 13,000. 13,000. We're good. And that shows you that your max moment is right here. It's at this support. And that's going to be typical of your cantilever beams, and that's 13,000 foot-pounds, and that's what you will design. If it is a reinforced concrete beam, you will put reinforcing on the top to go for 13,000 pounds. The reinforcing on the bottom will just be temperature reinforcing or whatnot.